welcome to the third day of IEEE CloudNet. As we have done throughout the conference, open the day with a keynote. We have another exciting keynote today. Bruce Davie from VMware will be talking about network virtualization for enabling software-defined data centers. And he joined VMware as part of Nicira acquisition, where he was on a journey to change the way networking is done. Before that, he was Cisco fellow, he doesn't need much introduction. So standardization on MPLS, IPQoS and things. And he's an ACM fellow as well. And long time back, he actually close to when I did my PhD, did his PhD from University of Edinburgh as well. So welcome, Bruce, and the floor is yours.
Thank you.
Thank you.
Well, good morning, and I guess congratulations on being the hardy few who've made it through the last morning of the conference. Yes, I'm going to say a few words about network virtualization, which is the technology that we've been developing at Nicira for some years, and you know, as Deep said, we're really in the business of trying to change the way networking is done. And it's actually very appropriate to be speaking at this conference because the real problem statement for us was trying to remove networking as a bottleneck for cloud systems or for cloud computing. And so hopefully you'll get a sense from this presentation about how we're going to change networking to make the agility that we've come to expect from the cloud available in the networking world. So just a little bit of sort of history here. The fundamental technology that enabled cloud computing really was server virtualization. And before server virtualization, if you wanted a server, you would just order a box, and you would place your order with some company, and they would probably manufacture the box and ship it and send it off to you, and then it would turn up in your lab or your data center, and you could get it installed and plugged in and configured with some software, and eventually 10 weeks or so later you'd have a server ready to run your applications. What server virtualization did was it changed the model from one where you had to order a box to one where you would have a pool of computing capacity sitting in the data center all ready to go, and whenever you wanted a new server you would just provision a new virtual machine. So that is a process that's now highly automated, typically done using some kind of software tools, and the provisioning of a virtual machine now typically takes on the order of a couple of minutes. And so many people think of server virtualization as having been all about consolidating multiple physical workloads onto a smaller set of physical machines by virtualizing those workloads. And that's true that the initial return on investment calculations that people were doing for virtualization were all based on the idea that I could go from having multiple physical servers to having a smaller number and consolidating workloads. But that was how we got virtualization off the ground, but the really big win was actually this change in the operational model. And so this is great. Now you can sit at your desk, push a button on a cloud management platform and spin up a VM and be off and running with an application. Unfortunately, many other aspects of the data center have not kept up with this. And so, when you're doing computing, you don't just need a CPU, you also need some storage, you need some networking, you probably need it to be connected to some firewalls, some load balancers, some security services. All of these things need to be done, and these things still need to be provisioned. And so, much as it's great that we've shrunk the time that it takes to provision a new virtual machine, with most of today's traditional technologies, it's still a lengthy process to provide everything that you need to bring up a new computing environment. So let me give you a really concrete example of this. So one of our early customers was eBay. You all know eBay as the online auction house. They're a very large software development house as well, because they're continually developing new applications. And eBay embraced the technology of virtualization, and they were in exactly this position of being able to provision virtual machines with just the click of a mouse, and every developer who wanted to start working on a new application could bring up his own compute environment, without ever having to talk to somebody in IT, because he would do it all through software tools with some kind of automated front end. But then after the virtual machines were provisioned, they would then hand off a trouble ticket to the networking group, who would then go and provision all the networking things that needed to go along with the compute resources. And actually a fairly heroic amount of work went into shrinking the time to deploy all the networking services to get it down to 7 days. And often when I tell this story, people say, yeah, 7 days to provision the network, not bad actually. Firewalls, VLANs, access control lists, all those things have to be done. There's change control processes. You want to make sure you don't make any mistakes. So there's a lot of process that goes into provisioning all those networks, and hence, 7 days is actually pretty fast if you're doing it with traditional networking. So our vision of the future is to get that 7-day, or in many cases multiple week process of provisioning all these additional networking services shrunk down to a matter of minutes, just as we've done for computing. So the idea now is that you provision not just a virtual machine, but a virtual data center. And this is the vision that we often refer to as a software-defined data center, where everything that you need is now provisioned in software. It's virtual machines, virtual networks, virtual storage. Everything is created in software containers and can be automated. So let me say a little bit more about how this is actually going to work. So, I've sort of given you a high-level view of what's wrong with traditional networking, but let me say a bit more about this. So you bring up your virtual machines, and those virtual machines have some IP addresses and some MAC addresses, and you want them to be able to talk to other virtual machines. So in order to do that, you need to actually go and touch some physical networking devices to connect the virtual machines to the correct subnet. You probably need to provision a VLAN to isolate these virtual machines from some other virtual machines. You might need to put in some access control lists to limit the connectivity between one set of nodes and another, put in some firewall rules to protect against possible security concerns. All of these things are manual steps, traditionally, that require the configuration of a particular physical box. Now you've configured these physical boxes and you decide you want to move that virtual machine from one place to another, which is one of the great things about virtualization, is you can migrate a virtual machine from one location to another. But if you do that, everything that you just did to the network is now being done in the wrong place. And so you run into problems of mobility and problems of workload placement, because everything that was done in networking was physical and it was tied to particular pieces of physical hardware. Furthermore, the capabilities that you get out of the hardware are whatever the hardware delivers. So you might have bought your switches from some particular vendor, they have a certain set of capabilities, and now one day you decide you'd like to upgrade to a new set of switches. Well, you're going to get a different set of capabilities. So you're sort of locked in with a particular set of capabilities. So the whole thing is quite operationally intensive, quite inflexible, and effectively undoing a lot of the goodness that was provided by server virtualization. So the answer to this is to do for networking what we've already done for computing. So compute virtualization provides this sort of abstraction layer that decouples the virtual machines from the underlying compute hardware. Network virtualization has a similar abstraction layer that enables us to decouple network services from the underlying hardware. And all the problems I described are addressed by network virtualization. Probably the most important thing is we move from a world where configuration is a task that involves typing into the CLI on a box. We move into a world where configuration is done in software, which means it can be done by automated tools. And I'll say a lot more about how we actually make this work in a few minutes. So let's go a little bit deeper on the analogy between network virtualization and server virtualization. So I mentioned here that it's a partial analogy. Actually, all analogies are partial, right? That you use an analogy to help you understand something, but it doesn't actually define the thing that you're using in the analogy. So let me just sort of say where the analogy works. And people often say, well, network virtualization is not like server virtualization in certain ways. I completely agree. But there are some ways in which there's a great similarity. So in server virtualization, you start with some general purpose hardware, and the requirements of that hardware are fairly generic. So you can take essentially any x86 based server that conforms to sort of the basic properties of a server and put a hypervisor on it. And that hypervisor abstracts away the specific details of the underlying hardware and provides a uniform model above, which is the virtual machine. And so you can now take your operating system and your application and put it inside a virtual machine, and it's completely decoupled from the underlying hardware. So the first point is decoupling. And then the other thing about a virtual machine is it is a complete, faithful reproduction of a physical x86 machine, which is to say it so completely reproduces what you could get from physical hardware that the applications actually don't know that they're running in a virtual environment. And so this sort of second key property of server virtualization is the faithful reproduction of the capabilities of the underlying hardware. So decoupling and faithful reproduction. So the same thing is done in network virtualization. We start with general purpose networking hardware, which provides a basic set of services. And in the case of networking, we start with switches and routers that can transport IP packets. So we don't require a lot of specific features. All we really require is that the network hardware can transport data from point A to point B. And that's our sort of basic infrastructure, and then we lay the network virtualization layer on top of that. And then on top of our abstraction layer, we now create virtual networks. And virtual networks are software containers that completely reproduce all the properties of physical networks. So in a physical network, you could have L2 bridging, L3 routing, some firewall rules, some access control lists, all kinds of features. Those things have to be reproduced in the virtual network. So the idea here is that a virtual network is going to be a complete, faithful reproduction of a set of services that historically would have been provided by hardware, but they're done in a way that is decoupled from the underlying hardware. So those are the sort of the key properties of network virtualization. So now that I've explained to you why we need network virtualization and given you a rough understanding of what it is, let me explain how it can be implemented. So one of the key technologies that underpins network virtualization is virtual switching. And if you look at a hypervisor, you'll find inside every hypervisor there's a virtual switch. And that virtual switch is there because that hypervisor has virtual machines running on top of it, and those virtual machines need to communicate with each other. So they'll do that by communicating through the virtual switch. And they also need to communicate with the outside world. So anytime a virtual machine sends a packet, whether it's to another VM in the same server or to the outside world, the first networking device that sees those packets is the virtual switch. So an interesting thing about virtual switches is that they've become extremely prevalent because hypervisors have become extremely prevalent. And so according to this data that was collected by an analyst, the number of virtual access ports recently exceeded the number of physical access ports. So if you think of all of the switching hardware deployed in the world, it's growing at something like 15% per year in terms of number of ports. But as people virtualize more and more workloads, the growth rate of virtual switch access ports is growing at something like 32%, and as a result, those lines have now crossed. So there are actually more switching ports deployed in software than in hardware. So as you can imagine, this is a pretty interesting statistic for somebody at VMware, since our core business historically has been hypervisors. So and of course, we deliver virtual switches as part of the hypervisor. And when I was at Nicira, before we were acquired by VMware, one of the big things we worked on was the open virtual switch, Open vSwitch. So between those two, the VMware vSwitch and the OVS vSwitch, probably most of those virtual access ports are actually software that we develop. So at some level, we became a networking company without even realizing it, because that's the data. We're seeing, the first packet out of every VM is going through a piece of software that is in our product. So just to make this sort of a little more clear, and I'm going to start sort of building up a picture of how we start with a virtual switch and go from there to a virtual network. So as I said, the vSwitch runs inside the hypervisor, and it's there to essentially process packets as they're entering and leaving virtual machines. And then sitting sort of underneath the physical servers is some physical network. So bear in mind, the physical servers provide us with a pool of computing capacity, and on top of that we create virtual machines. The physical network provides a pool of networking capacity, and on top of that we're going to build virtual networks. So the virtual switch is an important component here, but it's by no means the whole story. A helpful analogy, if you're a traditional networking person, is to think of the virtual switch as being like the line card. It's the thing that actually processes the packets in real time as they come in and out of the virtual machines. But to build a complete virtual network, you're going to need something to control those line cards. So let's have a look at how this works. So as I mentioned, we're involved with a couple of different vSwitches, one of which was developed as part of the VMware hypervisor, vSphere. The others developed as an open source project, Open vSwitch. So from the perspective of virtual networking, we actually don't care what the hypervisor is, as long as it has some kind of virtual switch that we can control. And the real brains of network virtualization is the controller cluster. So you'll notice I've made it this far into my talk without saying anything about SDN, which is something that I can actually normally go an entire hour without mentioning, but I'll mention it for this audience, that you can think of a controller cluster as being, in some senses, like an SDN controller, in the sense that it provides a centralized point of control for a distributed data plane. So the controller, and I'll say more about how the controller cluster works in a few minutes, but the controller cluster is the brains of network virtualization, and it's the mechanism by which we're able to provide this abstraction that decouples virtual networks from physical hardware. So anytime we want to create a virtual network, we're going to talk to the controller cluster. And we do this through a northbound API. And that northbound API is typically consumed by some kind of cloud management platform. So a cloud management platform might be something like OpenStack or CloudStack or some other cloud management platform. We develop our own at VMware. Not terribly important for the purposes of this discussion, other than to understand that there's some piece of software that consumes this northbound API. And that's really critical when you start thinking about automation, because what we need to do to sort of realize all of the objectives that I laid out at the start of the talk is we need to be able to automate the process of creating and managing virtual networks. So I'll tell you another story about how virtual networking is being used in the real world. So I mentioned the story of eBay and the problem that they had with getting application developers up and running quickly. So we have exactly the same issue in our own engineering organization at VMware. So we run a system exactly like this for our own engineers. And so I can sit down at my desk and log in to a cloud management platform. It happens to be based on OpenStack. And I log in as Bruce Davie, and once I log in, I see that I have a certain quota of virtual machines and virtual networks. And I log into the cloud management platform, and there's a fairly typical configuration that an engineer in our group needs. So I can just push the button that says, please spin up the typical VMware networking engineer configuration. And it will bring up something like a dozen virtual machines and then connect them up into a virtual network. And under the covers, what's going on is the cloud management platform has a template of this typical configuration, and it spits out a whole lot of API requests into the controller that then takes care of creating that virtual network. So that's kind of the typical usage model that now means that I can create a complete software development environment with a dozen virtual machines connected into some kind of interesting network topology in a matter of a couple of minutes. So what I want to do now is explain to you a little more about how that works. So these API requests come into the controller, and the controller is actually, it's a cluster of machines and I'll explain more about that in a moment, but it provides a logically centralized point where I can send API requests. So instead of having to go and touch a whole lot of physical networking boxes, I just send API requests into this controller. So there'd be an API request that says, create a logical L2 segment. Another request could say, create a logical router. Another one says, connect a virtual machine to this particular segment. And all of these API requests are being generated by the cloud management platform. So eventually, the controller cluster builds up an abstract picture of the virtual network that's required by the end user. And so, in this example, there's a bit of L2, there's a bit of L3, there's some firewalls, and there's a couple of virtual machines connected to the virtual network. So at this point, those virtual machines are located somewhere on particular physical servers. So the controller cluster has this picture of the desired virtual network state, and it also understands the physical hypervisor topology. And so it is notified that these two virtual machines are located on particular servers, and it can now go and program the vSwitches on those two servers to create the necessary forwarding state to build that virtual network. So the job of the controller cluster is essentially a state management problem. You build up abstract virtual network state by sending in API requests, and then the controller cluster looks at the physical topology of the hypervisors and programs the necessary vSwitches with the appropriate forwarding state to create the desired abstract network state. So hence my comment that this is the sort of the brains of the operation, because it's doing all of this state management of mapping between the desired state and the actual physical world to create the necessary forwarding state. And then if at some point one of those virtual machines were to migrate from one server to another, then the controller would be notified that the virtual machine has now moved, and it would now go and program a different vSwitch with the appropriate set of forwarding rules to maintain the desired abstract state of the virtual network in a seamless way. Now at some point, it's time to forward packets, and so as a packet leaves a particular virtual machine, it's going to hit the vSwitch. The vSwitch has been programmed with all of the necessary state to process that packet correctly, and part of that processing will include putting a tunnel header on the packet. So those thick blue lines at the bottom represent tunnels, and so now the packets get tunneled from hypervisor to hypervisor. This is the mechanism by which we decouple what's going on in the physical network from what's going on in the virtual network. So now you can do a whole lot of things in the virtual world that are independent of the physical world. For example, I can have an IPv6 address space in my virtual network and IPv4 addressing space in my physical network. Or I can have overlapping addresses between different virtual networks that are not visible to the physical network. And so we've essentially now achieved that goal of decoupling what's going on in virtual space from what's going on in physical space. So this kind of covers the basics of how you build virtual networks that are interconnecting virtual machines. But in the real world, there's lots of machines that are not virtual, and you need to get traffic in and out of these virtualized data centers. So we need some kind of gateway device that can map traffic from the physical world to the virtual. And we have a couple of different flavors of this. One of them is what we call the NSX gateway, which is essentially just a dedicated server with a vSwitch on it that can receive tunneled packets, and then under the control of the controller, it maps the packets out onto a physical link, such as a VLAN. So that provides a way that you can now build virtual networks that span the physical and the virtual. Now, when you start getting into more high bandwidth environments, you might not want to do all of your forwarding through x86. And so we've also partnered with a number of hardware companies to implement a thing called a VTEP, which stands for VXLAN Tunnel Endpoint. And that enables us to do essentially the same thing as we were doing in the software gateway, but to do it using a hardware switch, again, under the control of the controller cluster, so that we can program these hardware devices to map traffic from the virtual world into the physical world. And typical use case for this is you might have a rack of physical machines, maybe running your database application, and you can now connect those racks of physical machines into the virtual world. So it gives you a bit of an idea of roughly how we've implemented the virtual networking abstraction and how we've managed to decouple everything that goes on in the physical world from the virtual world. So one of the things that people often worry about when they see a picture like this is, well, isn't that centralized controller a bottleneck? Mm-hmm. So the first thing, and I use the SDN word perhaps ill-advisedly to mention that, what the controller cluster is doing. One of the things to realize is no data packets go to the controller cluster. The controller cluster is completely receiving its desired state from that northbound API. So there's never a need for a data packet to go to the controller cluster. As soon as a virtual machine is spun up, the controller cluster programs the vSwitch to handle the first packet that's going to be sent by that virtual machine. So we never see data packets in the controller cluster. But the controller cluster still has to do a lot of work. There we go, I have a pointer right here. So the controller cluster is doing a lot of work because basically it's receiving all these API requests, and it is potentially managing very large amounts of state, particularly if you think of a large data center where virtual machines could be getting moved around with fairly high frequency. So the important aspect of this is you need to build this in a way that it scales. And this is actually sort of a lot of the hard work that goes into building a platform like this, is providing a logically centralized abstraction while at the same time making it have a very high level of scale. So let me explain a little bit about how we scale the controller. And to me, this was actually one of the most exciting things that I discovered when I started working in this field, is that we've transformed the world of networking into the world of distributed systems. Mm-hmm. Because we still run distributed algorithms, but we don't run distributed algorithms on routers anymore. We run them on x86 servers that are very high performance and connected in very tight clusters. So we get to use kind of all of the distributed systems techniques that are used by people like Google and Facebook to build their extremely scalable data centers. We get to use those techniques to build the central point of networking control, rather than having to build distributed algorithms that run on all kinds of routers, distributed over lossy links, running with perhaps very limited CPU power. And so we essentially provide ourselves the ability to use a whole new set of tools to build scalable distributed systems. They're not new to the distributed systems community, but they are new to the networking community. So the controller is, as I said, it is logically centralized, but it's actually a distributed system. So in most deployments, we run with 3 controller nodes. So by having 3 nodes, we've immediately got around the point of having a single point of failure, but we also distribute the work evenly amongst the nodes in the cluster so that there's the ability to scale out the cluster as the amount of work that we're asking it to do becomes greater. So to give you a sense of the scale here, today we have this running in data centers with thousands to tens of thousands of physical servers and hundreds of thousands of, or at least many tens of thousands, approaching 100,000 virtual machines. So the controller is in the job of managing tens of thousands of logical ports and thousands to tens of thousands of physical vSwitches running on physical boxes. So there's a lot of information that the controller has to deal with. So we distribute the work amongst the different nodes in the controller. And so for example, for any one vSwitch, that vSwitch lives on a particular hypervisor. And so one node in the controller is going to be responsible for keeping track of what the proper state of that vSwitch should be and programming that vSwitch as that state is updated. Similarly, for every logical network, we're going to have one node in the controller cluster that is responsible for keeping track of the desired state of that logical network. So that's kind of a pictorial view of how we distribute the work for these different tasks out amongst the different nodes in the controller. And something like the the web service API that enables us to actually field API requests, that's a service that's replicated on every node, but the more intensive tasks like keeping track of what the vSwitches are doing is actually fully distributed across the nodes in the controller. And so if we just stick with the example of keeping track of what one vSwitch should be doing, there's one node in the controller cluster that's responsible for keeping track of that. But if we lose that node, then another node in the cluster will pick up the work and start doing it. And then at some point, if we need to scale the system up further, we just add some more nodes into the controller cluster and we spread the work out further. So we avoid having any single bottleneck in terms of performance. And as I said, if we lose one node, then all of the work that was being done by that node gets reallocated to other nodes. And another nice property about this is that you can upgrade the software on a node. You take that node out of service, the other nodes keep running, you upgrade the software, that node can now rejoin the cluster, and you keep on doing that one node at a time until you've got a completely upgraded cluster, completely non-interrupted. So I want to talk a little bit about tunneling. I mentioned a couple of slides ago that tunneling is one of the sort of base level technologies that we use to separate what's going on in the virtual world from the physical world. I think a lot of people in the traditional networking world get obsessed about tunnels because we understand them. They're packet headers, and we're packet header people. So I want to kind of give you one important message about tunnels. They're not that important. They're an important mechanism. You have to have them, but the details don't matter that much. There's so many different types of tunneling, and people love to have arguments about the best kind of tunnel. So I came up with this analogy that a tunnel is really like a cable. So, if you're wiring up a physical network, in some places you might use category 5 twisted pair, in other places you might use single mode optical fiber, and there are various different types of cable. And you want to pick the right one for the job. But nobody would claim that my network architecture begins and ends with my choice of cables. So the same is true for tunneling. It's a low-level detail. It's important to choose the right one, but it's not the fundamental architecture of the whole system. So in our environment, we use a couple of different types of tunnel primarily. VXLAN is the one that I think many of you will have heard of that has been adopted by most of the industry at this point. And so we use VXLAN extensively for tunneling between hypervisors and third-party switches. And so, I think most of the major switch vendors now support VXLAN tunnels. We also use a different type of tunnel called STT for hypervisor to hypervisor traffic. And the reason we use that is because there's a feature of today's network interface cards that means that they typically don't provide the same level of performance when you're using tunnels as when you're sending unencapsulated traffic. And STT was a tunneling format that was invented at Nicira that enabled us to maintain the high performance offloads that are available in today's commodity NICs without giving up on having a tunnel encapsulation. So it's a little bit sort of having your cake and eating it too, that we get to put on a tunnel header without losing the high performance of today's NICs. This is a short-term thing that within a couple of years there will be high-performance NICs that you can already buy them today, but they're not that widely deployed, that will provide high performance for VXLAN as well. So this is what I mean about it being important to choose the right tunnel for the job, but it's not the fundamental architecture. The architecture is what I showed you in the last couple of slides before this, and the tunnel is a little bit of detail. So one other thing I want to talk about is how scaling works in the data plane. So I've given you a little bit of a flavor of how the control plane can be scaled by implementing a distributed system to provide this sort of logically centralized controller. But it's also very important that we distribute the data plane. So one of the great things about network virtualization is the way we're able to leverage the huge amount of x86 computing capacity that's in the data center. Right? You've got all these servers sitting there with virtual machines running on them, and there's a vSwitch sitting there in every server. So we're essentially providing all of the features of the network in those x86 devices. And x86 is not the technology that you would choose if you were trying to build a high-performance service provider class router. But if you're running virtual machines, you're definitely going to run them on x86 or, you know, with 99% probability. And so, and you have to get the packets out of those virtual machines onto the physical network anyway. So we're essentially leveraging the existence of these vSwitches to provide all of the sophisticated networking. So one of the things that's really important is that we need to be able to fully leverage those vSwitches so that we can get the sort of the scaling benefits of having a vSwitch everywhere. What you don't want to do is to have to send traffic off to a particular box to get a particular service. So a good example of this would be a firewall. Traditional firewalls are implemented in a centralized way, and there are good reasons for that. It's much easier to manage a centralized firewall, and you provide this sort of central choke point in which all of your traffic passes so that you apply the necessary security policy. So that's good from a policy point of view, but it's not really good from an implementation point of view because you've created this central bottleneck. You now have a problem of how do you scale it up from a performance point of view. You've also got problems of like, what if I messed up the routing and some packets didn't go to the firewall? And there's also the challenge of just making sure that all of the packets actually get the appropriate services applied. So this is kind of the overall justification for distributing services. And what I'm going to do in the next couple of slides is I'm not going to show you the firewall example because it's a little bit more complicated, but I'll show you how we build a distributed router. And the same basic idea would apply to firewalling. And the overall philosophy here is every function should be implemented in these vSwitches without ever having to hairpin traffic off to a central box. And this is also, I think, important to understand in the context of what I said at the very beginning about network virtualization. This is not just about doing some kind of stretched L2 across L3. This is about completely reproducing all of the services that you could get from a physical network in the virtual network. So we have to be able to do everything from L2 through L7 in these vSwitches, and as much as possible, we want it to be fully distributed. So what I'm going to show in this example is a logical topology up on the top left there. We've got a logical router, a couple of logical switches, and some different tiers of a multi-tiered application, the web tier and the application tier. So that's the logical view that we're trying to create. And then down here is the physical view. We've got a bunch of hypervisors with vSwitches. We've got a virtual machine corresponding to the web tier and another virtual machine corresponding to the application tier. And so the objective here is to be able to forward a packet directly from one VM to another, apply all the necessary services to it, and not have to take it off on some hairpin to some extra device. So you want it to follow the shortest path through the physical network with all of the services being done in the vSwitches at the two ends of the path. So essentially the way this is done is that logical topology is created by, again, sending API requests into the controller. The controller does a set of calculations to figure out what do the vSwitches need to do to implement this fully distributed policy, and then it programs the two vSwitches at the two ends of the tunnel to implement that policy. And so the vSwitches get programmed, and now when a packet gets forwarded, it's going to get the L2 function of the first logical switch, the L3 function of the logical router, and the L2 function of the second logical switch. All of those are going to get applied at either one end or the other of the tunnel as it passes through the two vSwitches. So in this example, I'm sending a packet from the web VM to the application VM, and you should look at the MAC addresses here. This is the MAC address of the VM. This is the MAC address of the router. So the web VM understands it's trying to send a packet to an IP address that's on a different subnet. It's got a default router that it would probably learn about through DHCP. It would send an ARP packet to learn the MAC address of that router, and at some point it has the MAC address ready to go, so it creates the packet and sends it. The packet hits the vSwitch, And the vSwitch has been programmed by the controller to implement, in this example, the logical routing function. So now as the packet heads out from the vSwitch, you'll see the MAC addresses have changed. The source MAC now is the MAC address of the router. The destination MAC is the MAC address of the application VM. And again, there was probably an address resolution step to learn that MAC address. And then finally, the vSwitch puts a tunnel header on the packet to send it off to the correct destination. Now the packet can travel across the physical network, arrives at the destination hypervisor, is picked up by the vSwitch. The vSwitch looks at the tunnel header. That enables that vSwitch to understand what logical context this packet belongs to, so we can tell one virtual network from another. It now sees the destination MAC corresponding to the application VM and delivers the packet. So you can see how we had a fully distributed pipeline there with a bit of L3 at one end, a bit of L2 at the other end, and this enables us to do all kinds of distributed services using the same basic mechanism. All right, so the final thing I want to talk about before I wrap up is how we connect the physical world to the virtual world. And I touched on this earlier, so let me just give you a little more detail about how this works, and then I'll move on to conclusions and Q&A. So remember, the problem we're trying to solve here is that the world is not 100% virtualized, much as VMware might wish it to be otherwise. There's physical machines that have to communicate with virtual machines. And so at some point we reach the stage where we need a high bandwidth mechanism for connecting the virtual world to the physical world. So we've worked with a number of hardware switch companies and developed an API that runs between the controller cluster and the physical switches to describe the abstract behavior that we want out of these physical switches. And you might wonder why we didn't use OpenFlow for this if you're an SDN sort of person. And the reason for this basically is because OpenFlow specifies a very specific forwarding model that the switch has to implement, which the majority of switches today don't implement. So we picked a different protocol, which is called OVSDB. It's the Open vSwitch Database Protocol, which is a protocol that we've been using for some years to configure vSwitches. And so in OVSDB, we can basically specify the desired behavior of a switch without requiring a particular forwarding pipeline. As long as the physical switch can forward packets onto VXLAN tunnels, we can specify the desired behavior using OVSDB. So that's the mechanism that we use. OVSDB is actually a database protocol that lets us just create tables and read and write information in those tables. So just as before, if we want to create a network that spans the virtual and the physical, a series of API requests will come into the controller cluster and it will build up a mental picture of the desired network state. But now, in addition to programming vSwitches, it's going to write some information into the database that's residing on the physical switch. So the database is sitting over there, and there are many things that get written into this database, but one of them is information about the virtual machines. So as the controller cluster learns the location of virtual machines that are in this particular logical network that's trying to create, it will write that information into the database. So it's now available to the switch. The switch, meanwhile, is connected to the physical world, and so it learns about what's going on in the physical world. And it can do traditional L2 learning. It learns about the MAC addresses of the physical devices, and it can write those into the database. So this database is just a table that is accessible to both the switch and the controller. And eventually there's enough information in that database that enables the switch to build a set of VXLAN tunnels, and now it can communicate with the necessary hypervisors to forward packets onto the appropriate VMs and effectively implement that logical network that's shown at the top. So this has proven to be an extremely effective way of working with third-party hardware. We've now done this with about 6 different hardware partners, and we're adding more all the time, because it provided a very simple abstract model that essentially everybody who could do VXLAN could implement this, and it didn't require us to go into sort of low-level specification of the forwarding pipeline. So just want to spend a couple of minutes sort of talking about what's coming next. So one thing you should realize is that network virtualization is basically about transforming networking from a hardware operation to a software operation. And a virtual network is now a collection of bits, just like a virtual machine. Probably many of you have virtual machines, probably sitting in files on your laptops right now. If you run something like, VMware Fusion or Parallels, you've probably had a virtual machine, you save it to disk, and then sometime later you could put it on a different machine. It's just a bag of bits. The same is now true for network virtualization. The entire state of a virtual network is just a set of bits. So we can do all the sorts of things that we do with virtual machines. We can create a snapshot of a network. We can take that snapshot and we can ship it somewhere else, recreate that network, do some tests on that network, and ship it back. We've done exactly this with some of our customers. We basically get them to send us their current network as a file. We bring up that network in our test environment. We make some configuration changes, maybe upgrade to the latest version of software, make sure everything's working, and send back the file. So the entire network is now represented by a set of bits. So all sorts of things that you couldn't do before with networking become possible. And I think we're just beginning to understand all the power behind this. Just like with server virtualization, when it first came along, people said, oh, this is great, I can buy fewer servers. And that was kind of it. But today, server virtualization has fundamentally changed the operations of data centers. It's the thing that enables Amazon to bring up virtual machines in no time at all when you swipe your credit card, because they don't have to go and touch physical boxes. I've really talked so far today about the single data center environment, but clearly in the real world, we're going to be dealing with multiple data centers. We're going to want to federate between data centers and build virtual networks that span the globe, not just a single data center. So this is an area that we're actively working on, and I guess time prohibits me from saying more about that, but simply to say, I've explained to you how it works in a single data center. Rest assured there'll be a lot more to come in terms of how this starts to span wide area networks and multiple data centers. I talked a little bit about how we're doing things to tie together the virtual and the physical. One of the important things that I didn't really talk about is, how do you troubleshoot what's going on in the virtual network? Well, some of what's going on is something that's very easy to troubleshoot because it's all in the virtual networking software, but some of it's actually in the physical network. So one of the things that is an active area for us is actually getting visibility into the physical network and also having control over the physical network to deal with things like congestion. So again, another area where we'll see a lot more is providing the right tools to manage the physical to the extent that we need to, while still trying to maintain all the flexibility of having all of our state in the virtual world. I talked a little bit about things like distributed firewalling. The basic capabilities that I described today are really all about tackling the entire networking stack from L2 through L7. And there are things we can do with these higher level services that are fundamentally very hard to do in physical networking, but much easier to do in virtual networking. Just give you one example. If you're sitting inside the hypervisor, it's actually possible to look at the operating system and figure out what's going on. You can see accesses to the file system, you can see what users are logged into that operating system. So now you can start doing networking policies that are based on what's actually going on in the end system. This is much harder to do in a firewall box that's sitting off in the network because you only have access to the packets. But in the hypervisor, you have access to the complete in-system environment. So you can start doing L4 through L7 services that are based on things like user identity or the application that are running. We can also start thinking about doing networking not based on configuration of switches and routers and firewalls, but speaking at a higher level about things like policy. So you might, rather than saying, I want to put in this firewall rule, you might say this group of users should not be able to talk to this group of users. And that's a high-level policy which can then be compiled down to a set of API requests that can be programmed into a virtual network. And another thing that's really interesting is that in a virtual network, we have enormous knowledge about what's going on because we have all of the state in one place. This gives us the ability to formally reason about what's going on in a virtual network. So we can apply techniques like header space analysis to say with complete confidence, this virtual machine cannot talk to this virtual machine. And maybe that's not what you wanted because you put up some access control lists in the wrong way. We can actually tell you that without ever having to send a packet because we can analyze the complete state of the network. So there's a whole lot of things that are enabled here, and I'm just trying to give you a flavor of like how much this capability really revolutionizes networking. So to sum up, what we're trying to do here is do all the good things that were done in the server world and bring them to the networking world. In many respects, I feel like networking is a decade or more behind the server world, and we're trying to catch up. You know, the fundamental thing that this is really enabling is a higher level of agility. But as you saw from my last slide, we're also enabling a whole lot of things that we probably didn't even think about, and will become more apparent as we sort of go through this adventure in more, you know, with more time and more use cases. Hopefully I gave you a good sense of how the system can scale, that you know, if you're going to make this sort of thing work, scale is really important. In fact, Eric Rosen, who's a famous networking guy who I used to work with, said, there's only one problem in networking, scale. If it weren't for scaling problems, almost anything would lend itself to a trivial solution. So addressing scale is fundamental, and hopefully I gave you a sense of a couple of the ways in which we're tackling that for network virtualization. And you know, the fundamental thing here is to move from a model of talking to physical boxes to a programmatic model where everything is done in software, which is that's the thing which enables all these new capabilities. So I have worked in networking for about 25 years, and right around the time that I decided to join Nicira, I was actually getting a little bit discouraged about networking. You know, this feels like a very mature field, a little bit like the way power engineering was when I was younger. It's like people don't go into power engineering if they want to change the world because it's fairly mature. I was beginning to feel the same thing about networking, but I no longer feel that way because I think we've actually got the opportunity now to really fundamentally change networking in very significant ways. I think it's the most exciting thing in networking in the last 20 years. Hopefully I've shared some of that excitement with you, and I thank you for your time.
Thank you, Bruce, and we have time for some questions.
Thank you, Bruce, so much. Very interesting talk, and thank you for the insight. It seems now like the vSwitch, we're asking it to do more than it was designed for, switching. You know, we're asking it to do routing, we're asking it to do firewall, filtering and things of that sort. Isn't that an issue? So are we moving in the future from vSwitch that is software-based maybe to hardware-based ones?
So it's a great question. So, you know, are we asking the vSwitch to do too much? The key here is that most of the cost of doing things in the vSwitch are to do with things like data movement, and you have to pay that cost anyway. You've got to get the packet from the VM to the physical wire. Clearly, there could come a point where if you were trying to do really sophisticated things like deep packet inspection in the vSwitch, it might become too much. Our sort of rough rule of thumb is as long as we're only dealing with the packet headers, then the vSwitch is the right way to do things. I think for super deep packet inspection, the vSwitch may not be the best place. But I want to stress the vSwitch provides fantastic scaling properties because as you add more servers, you get more vSwitches. And in general, our vSwitches today can easily saturate a 10 gig link. So there's not a real problem doing all these functions in the vSwitch today. The only place where we see the vSwitch as a bottleneck is in the gateway, because the gateway has a lot of potential fan in or fan out from many virtual machines hitting a single choke point. And that's the reason why we have a hardware option for gateways. But I think as long as you're looking at traffic going in and out of the virtual machine, the vSwitch is actually very well positioned, and the set of things that you can do in x86 is very rich, and we've also spent a lot of time optimizing the performance of the vSwitch, including that the Open vSwitch is a very, very programmable thing, And so it actually doesn't matter that much from a performance point of view whether you're doing switching or routing. It's just a header manipulation. And so what we're really focusing on is optimizing the vSwitch for generic header manipulation.
Hi, Bruce. So I'd like to take some issue with OVSDB. It seems to me to be the wrong design to use a database access protocol to do network management. It seems at some point you're going to have to deal with various issues in terms of transaction completion, and you would also like to be able to have your physical hardware and your virtual networking be configured using the same thing. So you don't have to kind of do this cumbersome context switch in your controller to try to control the physical and the virtual. Now, I know why it's there. I was there when it was put in. But I'm wondering, is this sort of an attempt to keep some sort of proprietary sort of block out? So, OVS is kind of controlled by something that other sorts of stuff isn't? Or what? Can you please talk about this?
Sure. So to summarize the question, have I stopped beating my wife? More seriously, the question is, why have we chosen OVSDB and are we doing evil things with it? So essentially, the choice of OVSDB was very pragmatic, and so we've used it for many years to configure vSwitches. It predates OFConfig, and it essentially it provides very similar semantics to OFConfig, but it's the thing that we had before OFConfig existed. So we've been using it to configure vSwitches for a long time. The reason that we chose it to control hardware switches, as I mentioned earlier, was the obvious alternative was OpenFlow, which really wouldn't have been a good choice for that job for reasons I mentioned, essentially because it dictates a particular forwarding plane. The big benefits that we've gotten out of using OVSDB are, first of all, that the controller already knows how to use OVSDB to do a set of things that include things like you have many different nodes in the controller, and you can occasionally be in a state where two different nodes might try to access a vSwitch at the same time. OVSDB provides natural mechanisms to prevent bad things happening when there are multiple different writers to the database. It is a database protocol. It provides consistency, transactional semantics, all the things you'd expect from a database protocol. So it actually provides some benefits in terms of actually enabling the controller to stay in a rational state. The other sort of surprise benefit was, because it's an open source implementation, we just point all of our hardware partners at the open source database implementation, and in 5 out of 6 cases, they picked that up, ported it to their hardware platform, and had it up and running very quickly. And so that was actually not a reason that we picked it. We picked it mostly to make life easier for us on the controller side, but it turned out to be enormously valuable. So in terms of proprietary lock-in, it's kind of the exact opposite of that, which is to say we picked an open source thing and leveraged the fact that it's open source. You made one interesting point though, which was that do we have to sort of context switch between the way we configure virtual switches versus the way we configure physical switches? The answer is yes, we do. The reason for that is because physical switches are very limited compared to software switches. Even a physical switch that runs OpenFlow supports a strict subset of what the currently released version of OVS supports. And so we always have to face this problem that hardware switches expose a different model than software switches. That's the problem we have to live with. So we kind of minimize that problem by at least having a common protocol that the controller already understands.
Hi, Bruce.
Hi.
So I have 3 questions here for you. One is you skip a little bit on the firewall product. Can you touch a little bit that the architectural, aspects of the firewall?
Yeah. So let me just take them one at a time if I can. So the first one is kind of say a bit more about the firewall. Conceptually, the firewall is not that different than logical routing. It's that we program a bunch of stuff into the vSwitch to apply firewall rules. The biggest difference between the firewall and the logical router is that the firewall is stateful. So it actually will look at things like the beginning of a TCP connection and use that to create some state for the reverse connection. And so that's sort of an additional capability in the forwarding plane that enables us to provide stateful capabilities there. But from 10,000 feet, it's still fairly similar to the logical routing in the sense that you tell the controller what you want, the controller figures out how that would be represented as a set of vSwitch forwarding rules, and then programs the vSwitch to implement that.
So it's same about the firewall. So in the roadmap, do you guys have like a, in the roadmap.
Sorry, I thought this was an academic conference.
Yeah. Do you guys have like a VM-based firewall for a cluster? Or
Yeah, so I'm going to refuse to use the word roadmap, but the firewall is implemented fully distributed in the kernel. It's not a virtual machine. However, if you would like a virtual machine-based firewall, there are many companies that will happily sell you one. And this is actually a really important point, that you can implement services in virtual machines, but that is not the same as virtualizing services. Because anytime you have a service in a virtual machine, you have to send the packets to that virtual machine, which is potentially a choke point. A really interesting way of doing firewalling is to put a virtual machine firewall on every hypervisor. And then you can actually do firewalling in the kernel. And then for some packets, you could say, oh, these need a little bit more inspection, so we'll send them to this virtual machine that can do deeper inspection. So that's actually what we do.
The other one is intra-VM IPsec-like tunneling. Do you guys have anything like this?
Yeah, so the question is, do we ever do IPsec tunneling? We do, and like I said, tunneling, not that interesting, but IPsec is an interesting tunnel type because it's secure, we think, and it is expensive. So we do support IPsec. It's typically used for extending virtual networks across the wide area where security concerns justify the processing cost.
Bruce, I have two questions. First one is more on NSX controller. When you put multiple sort of copies or whatnot, it seems to look like virtual router redundancy protocol. Do you see some similarities between that because of the copy and whatnot you are doing, or is more like a parallel processing system where when you have multiple controllers as a part of the central control?
Yeah, so I think the gist of your question is, what's the sort of what does the controller look like? What other systems could I compare it to? I would most say it's most similar to something that you might find in a data center running some kind of algorithm. I mean, I'm not sure what's the best analogy. It's a distributed system where we run distributed algorithms to do things like leader election and then divide up the work amongst nodes in the cluster. It's a little bit, I suppose, like a Hadoop file system in a way that there's a master that then divides up the work amongst different nodes in the cluster. So it is definitely it's based more on what I would consider sort of mainstream distributed systems technology rather than sort of traditional router technology.
Okay. The last question is, being an academic conference, I'll ask a question more on what, from your experience and what you have seen it, what did you like to see the academics do differently in terms of training beginning networking students so that they are better prepared for this? Because for some time, with networking courses, it almost become transport and not a lot,
Yeah.
So I'd like to hear your thoughts and quickly if you can comment on that.
Yeah, so what would I like to see networking students getting taught? So I think I would love to see a little more focus on distributed algorithms because I think these days we're actually finding it's easier for us to recruit networking people than it is to recruit good distributed systems people, partly because all the distributed systems people go to Google and Facebook. I think that this distinction between distributed systems and networking is something that is sort of breaking down, and so that's something where I think just shooting from the hip here, I would say that's probably one area, I also say, I guess, as you probably know, I've written books on networking, and what I always thought was important is you try to teach fundamental principles rather than teaching artifacts. And I think there is still a tendency to teach artifacts. BGP is fascinating, in terms of how it's grown up over the years, but the set of fundamental principles underlying BGP probably shouldn't take more than 10 minutes to explain, and then all the cruft takes the remainder of several lectures. So that's a kind of a more generic point, but I think if you think about, what are we doing, we don't run routing protocols in the virtualized network. We don't need to. We know where everything is. But we have lots of complicated algorithms, and so that's probably the thing which is the most important.
One quick question. So I'm from Accenture. One quick question is, what do you think is the impact of virtualization of networking on enterprise?
That's a great question, what the impact is on enterprise. It is certainly much less obvious to me how this is going to play out in the enterprise. I think the opportunity to virtualize a lot of what goes on in the enterprise probably still exists, but if you think about what enterprise networking is all about, it's mostly about giving people connectivity, from remote offices into the main office and providing wireless access and things like that. There probably are opportunities for virtualization in that space, but it's much less clear at this point.
Bruce, that's a great insight and presentation. One question, OpenFlow is becoming a standard de facto for SDN. Where do you use OpenFlow in your system?
Yeah, the question is, where do we use OpenFlow in the system? And I didn't dwell on that because I think it's not that sort of low-level detail. But if you look at the packets going between the controller and the vSwitches, many of them are OpenFlow in the sense that when we program the forwarding state of a vSwitch, we use OpenFlow. That may not always be true, by the way, but it's what we do today because it's what Open vSwitch was built for.
Yeah, I was a little bit curious about what's the product for your central controller, because we're actually using the vSphere 5 in our system, in our classroom. So students actually have to configure vSwitch and the physical switch and all that. So I was just curious, is there anything that's readily available for university or college so students actually can play with it? That's one question. Number two question is, how do you secure those control cluster, because they are so critical?
Yeah.
If they, you have the reliability thing, but what if someone attacking your controller?
Yeah.
What are the protection there? Thank you.
That's two good questions. So in terms of what academics can do with this, as of today, we don't have an academic version of the product. So the product is called NSX, and NSX basically is a bunch of software that is sort of an add-on to vSphere, and it basically gives you the controller and the vSwitches and the gateway and all that stuff. So we don't currently have an academic edition of NSX. You certainly can play with VDS, the distributed vSwitch, which from a suitably high altitude is doing some of the same things that NSX is doing, but rather less sophisticated. I don't know if we'll have an academic thing. I'd be happy to follow up with you offline about that, because it seems like an obvious thing that we would want to do at some point. We are in the pretty early stages of this product. I hope that's clear. Regarding your security question, essentially the securing of the controller is one of the things that we use fairly traditional methods for. It's only accessible via its API. So it has very tightly controlled access. That API is authenticated using SSL. Similarly, if you look at the controller, there's like a connection out to the north where API requests are coming in. That's SSL. There's connections out to the vSwitches. Those are also authenticated using SSL. There are certificates on the vSwitches. So we use fairly standard things to sort of lock down all the entry points into the controller, and then we have our security team beat up on it.
So one last question, I guess. I finally get to ask a question as well. And I think I will ask a broad question where I was thinking about the statement you made about tunnels, right? Tunnels are like cables. And the reason actually we need to do tunneling is that there is lots of legacy, there is lots of restriction on the hardware and things. So if you had to actually had the opportunity to have a clean slate design where you didn't have to worry about these things, what would network virtualization look like? And would you do things differently?
That's a great question. So fundamentally, to do network virtualization, you need two address spaces, one for the physical and one for the virtual. And you need some way to decouple those address spaces. Tunneling is the mechanism that provides that. So you would always use some form of tunneling. And the question is, what would you pick if you had a clean slate? And I actually don't know what I would pick. That the sort of IP and IP tunnels that we use actually work pretty well. You could certainly make an argument in favor of doing something like MPLS. I could also make arguments against using MPLS, but that's actually one of the debates that's going on right now amongst people who like to debate things like tunneling. But there would be advantages to MPLS primarily in terms of the efficiency of the header and drawbacks in terms of the need for a control protocol to set it up. I would say no obvious answer to what you do with a clean slate, but I would certainly say it's fundamental that even with a clean slate, you would have some kind of tunnel encapsulation if we accept that MPLS is basically a sort of fancy tunnel encapsulation. Thank you very much.
Thank you.
There is a coffee break now. So.
We'll start in about 5 minutes or so later.
Yeah, so 10:35.
10,
10:20.
10, 20.
Here we go.